Hello. In this video, I'm going to show you how to perform some basic data transformations and build a time series model using R in Microsoft's Azure Machine Learning Cloud environment. For our purposes here, I'm going to define a time series in R as a set of values ordered and indexed by a time variable. I'll show you some examples of this as we go along, of course. We're going to build a model to forecast monthly milk production for the state of California. These types of time series models are extremely useful for a number of purposes. For example, you can forecast the optimal level of inventory, forecast demand, say for a utility or manufacturing, or make adjustments to macroeconomic data such as unemployment rates. You can find a great deal more about the models I'm going to show here in the Quick Start Guide that's available at this same website. If you have not yet already looked at the introductory video, I would encourage you to do that before you start on this. I have in front of me here the Azure ML Studio, and I'm just going to get a data set here. And there it is. cadairy-data.csv. I'm going to drag that onto my canvas. And then I need an execute R script module. And I'm just going to connect these two here. With this first execute R script module, we're going to perform some data transformations to prepare these data for further analysis in R. Looking at my RStudio, here's some code I've created for this first execute R script module. In this case, we're reading the data in either as a CSV file when we're in RStudio or using the MAML map input port function when we're in Azure Machine Learning. We need to normalize the coding for the month variable, so we're going to trim it to the first 3 characters and make it a factor. And we're going to remove some columns of the data we don't need. Next, we need to create a column which is the number of months from the start of the data set. And we'll use that when we build our time series model later. So I have this function here that does that. And I use that function and create a new column called month.count in my data frame. The next step is to perform a scaling and a log transformation of these data. The type of multiplicative time series model we're going to use requires the logarithm of the variables. So we will compute the logarithm here. We're also going to apply a multiplier or a scale factor because it turns out that some of these variables are in different units and we want them to all be in the same units. So we have this function here that does this. There's more detail on this, of course, in the Quick Start Guide, including a discussion of some of this code that's used to make this function robust for a production environment. We build a list of the multipliers for the unit conversion, and we use the map function here. So the map function allows us to apply 2 different lists, in this case, as arguments to the log.transform function and get the results back out into the data frame. We also then apply na.omit because we want to get rid of any rows that have NAs in them, and we check the results with stir and output to the output port. So now that we've discussed this code, let me uncomment this line, which is the one we use in Azure ML, and comment out the read.csv line. And then I'm just going to copy and paste into my execute R script module. Here, just like that. Okay, it looks like everything is set. I'm going to save this, and I'm going to run it. Let's have a look at the results. We can see where the output from the stir function, we got the factor we wanted with 12 levels. We have this new column, month.count, and we can look over here at this output and also see that month is now considered a categorical variable, which is exactly what we need. And we can see the numeric values of things like cottage cheese production, ice cream production, milk production, and the price of milk fat have been transformed to the logarithmic values. Now let's do something with this. We need to build a model. So let me get another execute R script module and drag it onto my canvas. Okay, I have this other code here that I'm going to walk you through. We'll read that data with this line of code here, just as we've done before. Now we're going to create a time series object. And there's a number of time series object systems in R, quite a few of them. And in the Quick Start Guide, I give some references to them. In this case, we're going to use one of the simple ones called POSIX CT, which measures time in microseconds from the start of the epoch, which was January 1st, 1970. We use this strip time function to create date times, and we get the year, we get the month out of our columns, and we don't really care much about what the minutes and seconds are because it's to the month. This bit here defines the formatting for strip time. If you're going to be working with dates and times in R, I strongly recommend you learn a bit about the strip time function. And you can see this is all wrapped in this as.posixct function, which gives us this time variable. Next, we need a training data set. So we're going to take the first 216 rows of this data, and that leaves the last year, the last 12 months out, which we'll use then to test our model at the end. Right, let's just try this little bit of code here and see how it goes. All right, again, just cut and paste. We can save that and then run it. Okay, let's have a look at the result here. I'm going to look here at what was printed by R. There was that stir function. We have this time variable, which is in fact POSIX-CT format. Exactly what we were trying to do here. So far, so good. Coming back to our studio here, I'm going to make some time series plots. And you can see that I'm using that new time variable as the one axis, and then I've got Y here as another. I also have a set of labels, so I've defined a list of labels here. And so by wrapping all that in the map function, I can have the list of the variables I want to plot and the list of those labels. And if we run all that, let's give it a try here, we'll get some time series plots. So going back to Azure ML here, and we're just going to cut and paste that bit of code, and we're going to save it, and I'm going to set the seed and run it. All right, so we no longer have the output from that stir function, but we do have these graphs. So we have the log of cottage cheese production versus that POSIX-CT time variable. We have the log of ice cream production, the log of milk production, and the log of milk fat price for Northern California. That looks very promising. All right, let's push ahead here. All right, let's go on to create our time series regression models. So I mentioned earlier we were building a multiplicative model, and that model has two components, and it's the product of those two components that's the complete forecast. So the first component is a trend, and the other component is the seasonal variation, which in our case will just be month to month predictable variation. So for the trend model, we have this line of code here, and we have milk production is modeled as that POSIX-CT time variable. That's our linear term. And then we have that month count from the start of the time series to the third power. That's wrapped in the I function, or Hibit interpretation function. So that function forces R to literally interpret this as that month count cubed. All right, so that's our trend model. Our seasonal model just adds the month variable. That's our seasonal component. The -1 means that we're not going to include an intercept term. Because we have these month components, if we included an intercept term, the model would be overdetermined and we'd lose one of our variables. Now we need to output these two models, and I've created a function here called serList, which serializes a list of our objects. Now these could be our model objects, as we'll have here, but it's much more general than that. It could be our data sets, our functions, lists of lists, etc. The one bit I want to call your attention to here is we use this serialize function, but it produces raw output, and Azure ML needs some other type. So we're going to coerce it to integer with as.integer, and we're going to call that a column called payload in our data frame. And so I build a list with our milk.lm model and our milk.lm2 model, and that's the argument to serList, and then I have outFrame, and that gets output. So let's go ahead and cut and paste the rest of this code to Azure ML. Okay, so looks like we got everything the way we want it. We'll save it. Let's run it. Let's see what happens. So at this port, we would just have those same graphics we had before. But let's look at what's coming out as a results data set now. And we see we have this one column called payload, and it has a number of values. These aren't really human interpretable. Remember, we've serialized a list of our objects. So now we need to do something with these models. So let me get another execute R script module here. And I'm going to connect the first port to that output. And we're going to take the output of our prepared data and make it an input also. Let me go back to RStudio, and here's our last bit of code. Now, we read a data frame called model frame from that first port. We're going to read the dairy data frame from that second port. And I have here another function that will unserialize those serialized linear models. And again, we have to convert this to raw before we give it to the unserialize function. And I have some code here that I check the class of those items in the list are both linear models, and if they are, I assign them to more convenient names. Now we need to do a little bit more data munging. We first off need to recreate that POSIX-CT time series object. Azure ML doesn't recognize that for what it is, and each time we pass data from one execute R script to another, we need to recreate things like that. Also, just to be on the safe side, I'm going to make sure that that month column comes up as a factor here. And then we're going to get our training data again, those first 216 rows of this dairy data set. And we can use the predict function on these two linear models to get two predictions, one just using the trend and one using the seasonal component. We can make plots of those, again, time series plots using that POSIX-CT time variable and against the production data. Then we use the lines function to make another time series plot, which are the predictions for the first and the second model, which will be superimposed on those plots. Okay, well that's quite a bit already, so let's just cut and paste all that in. All right, we're going to save that and we're going to run it and we'll see what happens. All right, we have a successful result. Let's look at the various outputs here. We see this is the milk production data, and we see that trend line, the red dotted line. Looks like it fits it fairly well. So we have the same milk production data along with the linear model, including the seasonal component. And again, it looks like a pretty good fit. Let us move on here. Let's make some predictions for the entire time series, including those 12 months that were not part of our training data set. This brings up an important point. If we have additional data and we don't want to rebuild our R models constantly, we can build the model with our training data, then serialize it, unserialize it as we've done here, and now we have an efficient way using the predict method for that model type to make new predictions based on new data without having to compute a new model each time. So now we have predictions for the whole data set for both models. We're going to compute the residuals manually here, and again make a time series plot of those residuals for the whole time period. And one of the reasons I'm doing this manually is because in this case I want the time axis to be the time axis I'm using so that my residuals come out in the correct time order. I'm also going to use the plot method on the model, which includes the seasonal variation. And note that I'm doing ask equals false here. If you're building code that runs in a production environment like Azure ML, you don't want the user to have to mouse click each time to go to the next chart. In fact, it may not even be feasible. I recommend you use ask equals false. All right, so now we'll have various diagnostic plots. So one last thing we can do here is compute the RMS error between the actual data and the forecast for those 12 months. This function here does just that with quite a bit of code added to make it robust, which is explained in the Quick Start guide. At the bottom here, we're going to use that rms.error function to compute the error for several different cases. Notice that I'm assigning row names here as the first column of my data frame. Azure ML does not preserve row names as row names, but we can preserve them by making them a column in our data frame. So that's exactly what we're doing here. And then we're going to output this. Let's go ahead and cut and paste the parts we haven't done now, and we'll put that into our execute R script function here. Voila. And just make sure everything looks good here. I'm gonna save it, and there's nothing left to do but run it. So now it's executed correctly. First, let's have a look at graphics we've created. So we've looked at these two plots already. Here's that time series plot of the residuals. And you can see there's no particular pattern here. We have this one dip, which was probably the recession, the 2008-2009 recession, which we didn't account for in our model. If we look at the standard residual plot, again, no particular pattern. This is nearly a straight line, this fit here. So that's pretty good. QQ plot plots the quantiles of a standard normal distribution against the residuals. They should ideally fall on a perfectly straight line, that dotted line, and you can see they're pretty close, so that's pretty good. Here's another plot of the standardized residuals. Again, it looks pretty random, just exactly what we're looking for. And this plot shows us some leverage points. And you can see there's a couple of little leverage points here, those ones with the numbers, but nothing that I would be concerned about. So it looks like we got a pretty good fit, but let's check what happened with the RMS error. Now you can see we have for the training data and for the forecast of those 12 months with a trend model or with the seasonal model. And you can see in each case, the seasonal model reduced the RMS error quite a bit. And as you would expect, the forecast has a slightly higher RMS error than the training data. Okay, I hope this video has been useful to you, and I hope you're ready to tackle some exciting data science projects using Azure ML and R. Thank you. Goodbye.